Hello everyone, welcome to module 11. So in this module we're going to talk about vibrations and waves. So in this module we're going to discuss four sections: simple harmonic motion, how to measure simple harmonic motion, properties of waves, and wave interactions. Let's start with section 1, simple harmonic motion. So in the first one we're going to identify the conditions of simple harmonic motion, explain how force, velocity, and acceleration change as an object vibrates with simple harmonic motion. Third, to calculate the spring force using Hooke's law. So let's talk about Hooke's law first. So one of the types of periodic motion is the motion of a mass attached to a spring. So let's consider three positions. So the position at equilibrium is the position where the spring is neither compressed nor enlarged. We are keeping it at normal state, at the resting state. Now notice that here, the position here, we call that the equilibrium position. Now when you stretch the spring, when you apply a certain force and stretch the spring, so that stretching of the spring vibrates this body between two positions. So the extreme position where the spring is enlarged and the compressed position where the spring is compressed to its maximum point. So the one point, these points are generally called as the maximum displacement points. So this is the maximum displacement and this is also the maximum displacement points. So the amount of distance traveled is a function of the elastic force of the spring. So this law is called as the Hooke's law. So the Hooke's law basically says that we know that at equilibrium the spring force and the mass acceleration become zero. So the speed reaches its maximum. So at this equilibrium position there is a maximum speed with no displacement and minimum, so there is zero acceleration. Now when you have at maximum displacement, the spring force and the mass's acceleration are at a maximum but the speed becomes zero. Notice that here the speed continuously goes slowly reducing and then becomes the maximum, it becomes zero and then comes back to its original value again at the equilibrium position. So this is the idea behind the top of the Hooke's law. So the measurements show that the spring force here is directly proportional to the restoring force, or the restoring force is directly proportional to displacement of the mass. So this displacement F, so this restoring force F is proportional to the displacement. When you remove the proportionality, F becomes negative Kx, where K here represents the spring constant and the negative sign is because of the fact that the force is always opposite to the displacement. So the force here is opposite to the displacement. So this is one of the reasons why we use the negative sign, because restoring force is always in the negative direction of the displacement. Now notice here that in the diagram, as the displacement is in one direction, it is in this direction, the elastic force being restored is in the opposite direction. The same thing happens in the reverse as well. The displacement is in this direction while the restoring force is in the opposite direction. So this is one of the reasons why we use the negative sign in the value of the Hooke's law. So this here is called as the Hooke's law. So this here is called as the Hooke's law. So let's take an example. So what is given here? If a mass of 0.55 kilograms attached to a vertical spring stretches the spring 2 centimeters from its original equilibrium position, what is the spring constant? So it has stretched elastic spring at its rest position to a displacement of negative 2 centimeters, and we are starting at the 0. So and you have the plus x as well in the opposite direction. Now they are asking us to find the spring constant. So we know the formula F equals negative Kx. So K becomes F by negative x. So now notice that x here is in the stretch. So if you consider this to be positive, so the upwards to be positive and downwards to be negative, so you have x becoming negative 2. So F here is the amount of force. So you have a mass of 0.55 kilograms. So if that is the mass that is stretching the spring, we can say that that is equal to mg. So mg is 0.55 times 9.81. So now let's take into account the elastic force here. So this is the Hooke's law right here. Now let's take into consideration the actual scenario in which this happens right now. So notice that here the weight is forward, the weight is in the downward direction. So this is the direction of the weight, and this is the direction of the elastic force, because notice that the elastic force stretches the spring in the opposite direction. So we are calculating the net force. So what is the net force? So the net force is the upward force minus the downward force. Upward force is Kf elastic minus the weight. Now we know that the net force is acting is 0, so which means equals to Fe minus Fg. So Fe becomes equal to Fg. So we know the elastic force is negative Kx equals the Fg becomes mg. Now x here, K here can be written as mg by negative x. So we have the mass value, which is 0.55 kg, g value, which is 9.81 meter per second square, and x, which is negative 2.0 centimeter. So which when converted to meter becomes negative 0.02 meter. So 0.55 times 9.81 over negative of negative 0.02. So negative negative gone. So we are left with 0.55 times 9.81 over 0.02. We have 0.55 times 9.81 divided by 0.02. So this value K becomes 269.775. So because the maximum number of decimals is 3, so we can round it off to 270. So notice that here we have to know the unit of K. So if F equals Kx, K becomes F by negative x. So we don't need to consider the negative. So the unit of force is Newton, the unit of displacement is meter. So the unit of spring constant is Newton per meter. So this is how you can calculate the value of the spring constant for the following problem. Next, let's talk about simple harmonic motion. So the motion of a vibrating mass spring system is a good example of a simple harmonic motion. So simple harmonic motion basically describes any periodic motion that is the result of a restoring force proportional to the displacement. So if force is proportional to the displacement, so all of these forces that describe this kind of motion, all of the examples that can describe this kind of motion is called as the simple harmonic motion. So because simple harmonic motion involves a restoring force, so every simple harmonic motion is a back and forth motion over the same path. For example, if you consider the displacement chart over time, so if you consider the displacement chart over time, let's say for example, in this axis we have the displacement. So in this axis we have the displacement. So let's consider the displacement here. So you have negative x on the opposite direct side, 0 and x. Now notice that we are starting at equilibrium. So the spring oscillates in such a way that it reaches plus x first. Let's say it reaches plus x after a certain amount of time, and then after a certain amount of time it comes back to its equilibrium position. So what will happen here? You have the body coming back to its equilibrium position and becoming negative x again. Again, you see that the waveform is called as a sine waveform. So if you consider the motion, the function of x and t to be a sine wave, we can call this a simple harmonic motion. So all of these types of motion are generally called as the simple harmonic motion. So another good example of a simple harmonic motion is the example of a simple pendulum. So let's take an example of a simple pendulum. Let's say we have a pendulum that's attached to a rigid surface. So let's consider you have a simple pendulum attached to the rigid surface. So let's consider this having a mass m. Now let's say we are tilting it over to a side an angle, and this, let's consider we're doing it over a small angle. So this angle right here, and let's call that angle theta. Notice that here at this position, what will happen right here? So let's have a mass m right here. Now this mass let's consider this mass m right here. Now at this position, so we call this, again, this becomes the equilibrium position. So this is the position of maximum displacement. So the same thing happens on the other side as well. So we are not going to draw that side, but remember that the same thing happens on the other side as well. This is the angle theta right here. Now at this position, we still have mass facing downward. So let's draw the free body diagram of this mass separately. So at this position, we are going to draw the free body diagram. At the second position, this position right here. So if this is the mass, so this is the mass m with its center right here. So this mass will have a force that is going downward. So this is the mass downward, so which is Fg. So this is Fg, which is again equals mg. Now you have another force, which is the tension of the string along the path of the string. So which can be written like this. So this is the tension of the spring. So tension P of the spring. So now you can take this angle right here. Let's say if you continue writing down this side, if you continue the tension of the string, because this line and this line are parallel to each other, and we are extending this line, so this angle here, so this angle right here, this angle becomes equals to theta. So because that angle is theta and we want to resolve this force, so let's resolve this force into two parts. So we get one force right here and one force right here. So this force, because it's attached to theta, so this becomes Fg cos theta, and this force, because it's attached again to theta, it becomes Fg sin theta. So from the free body diagram, we can say that this is the force. So now we have applied a force F right here. Remember that there is a force F right here. So that force F is the restoring force. So the restoring force acts in this direction. So F. So we also have Fg sin theta right here. So this is F and Fg sin theta. Now from the laws of mechanics, we can simply say that tension equals Fg cos theta. And this force, the applied force, so notice that here there are two forces. There is the restoring force and there is the applied force. So let's consider this is the applied force. So the applied force equals to Fg sin theta. So this is the applied force, which equals Fg sin theta. So because the applied force equals ma, becomes equal to Fg sin theta. We know Fg can be written as mg, so ma becomes equals to mg sin theta. Now let's consider the idea here is to remember that the force is directly proportional to the displacement. So how would you consider that to be the case right here? So we have to prove that the force is directly proportional to the displacement. So let's consider ma, which is the force, equals mg. Because the angle is really small, we know that sine 0 is 0. Because sine 0 is 0 and the theta is real value is really small, so we can say that for approximation sine theta is nearly equal to theta. So we can call that mg equals times theta. Now we have theta, so this is the arc length. So the arc length is displacement S, and let's consider this is the length of the pendulum L. We know that the arc is, so the arc times, so the angle is arc by radius. So we know that angle theta is arc here is S, over the radius is L. So let's consider X right here. So theta becomes equals to X by L. So F becomes equal to mg times X over L. So if you write this in such a way, oh, I'm sorry, we have to write the restoring force, not the applied force. So this is the restoring force. We have to write down the restoring force. So because it's on the same side, we can say that F as restoring equals negative Fg sine theta. So we are applying the restoring force right here. So it becomes negative. So we have negative mg by L times X. So notice that here, if you write down the Hooke's law, so which is negative kx, when you compare the two equations, you still get the same form, which is F proportional to X. So the force, the restoring force, is proportional to the displacement. From this, we can also write that K equals mg over L. So K equals mg over L. So which is again the easier understanding of the spring constant for a spring, for a pendulum. So even though the spring doesn't exist, the pendulum itself acts as a spring. The motion of a spring resembles the motion of the spring, so we can think of it that way. So what happens in terms of the simple harmonic motion right here? So at this position, so we are looking at the two watts of thinking about the force. At this position, the velocity is max and the acceleration is 0, because notice that here at this point there is no speed accelerating or decelerating, and at this point the acceleration is max but the velocity becomes equal to 0. So at the equilibrium position, the velocity is at maximum position and acceleration is 0, and at the maximum displacement position, acceleration is at the maximum value but the velocity is 0. So this is the idea behind the simple harmonic motion. So next, let's talk about how to measure simple harmonic motion. So first is to identify the amplitude of vibration. Second is to recognize the relationship between period and frequency. Third is to calculate the period and frequency of an object vibrating with simple harmonic motion. So let's start with the amplitude, period, and frequency in simple harmonic motion. So in simple harmonic motion, the maximum displacement from the equilibrium is basically defined as the magnitude of the amplitude of vibration. So when you consider the diagram where we talked about the sine wave, the maximum displacement here, A, is called as the amplitude A. So this is the maximum displacement right here. So the maximum displacement from the equilibrium position is called as the amplitude, and the pendulum's amplitude can be measured by the angle between the pendulum's equilibrium position and its maximum displacement. So for a mass spring system, the amplitude is the maximum amount of spring that is stretched or compressed from its equilibrium position. So the SI units can be either radian or meter. So in a simple harmonic motion, in pendulums, the angle between this angle right here, so the angle theta right here is the representation of the amplitude. And we generally calculate that in radian. For a mass spring system, the distance itself can be considered as the amplitude. Next, let's talk about period. So the period is basically the time it takes to complete one cycle. So one cycle means one back, one. So you start from the equilibrium position. So you go back once and then forward. So where you're talking about an equilibrium position right here. So you're going one back and then coming back to the position. So this here represents one cycle. So where you're going from the equilibrium position to the one extreme and then back again to the mean position. This here represents one cycle. If you consider it in terms of a sine wave, so one up and one down is considered as one single cycle. So that here is the period. So the SI unit of period again is second. Next is frequency. Frequency is basically the term that represents the number of cycles or vibrations per unit time. So the number of cycles or vibrations per second is basically called as the frequency. The SI unit of frequency again is hertz, which is basically 1/second. Now we know that period and frequency are inversely related, so which means frequency equals 1/time, or we can also write time equals time period equals 1/frequency. So if you know one value, you can always write down the other value. So what is the time period of a simple pendulum? So the period of a simple pendulum depends on two factors, the length and the free fall acceleration. So the time period T can be written as 2 pi times under root L over Ag. Ag here representing the free fall acceleration. So that this value Ag on Earth again equals G, which is 9.81 meter per second square. So T will be equal to 2 pi under root L over G. Now when you have a mass spring system, the formula for time period is 2 pi root m by k, where m again is the mass and k represents the spring constant. So the period does not depend on amplitude, and the equation applies only for the systems in which the spring obeys the Hooke's law. So that is about SHM and how to measure simple harmonic motion. Next, let's talk about properties of waves. So let's start with how to distinguish local particle vibrations from overall wave motion, differentiate between pulse waves and periodic waves, interpret waveforms of transverse and longitudinal waves, apply the relationship among wave speed, frequency and wavelength, and relate energy and amplitude. Let's start with wave motion. So a wave is a motion of a disturbance. So the difference between a wave and a vibration is the fact that vibration does not carry energy with it, but a wave does carry an energy with it. So a medium is a physical environment through which a disturbance can travel. For example, water is the medium for ripple waves in a pond. And waves that require medium through which to travel are called mechanical waves. Remember this, that whenever you see the term mechanical waves, which means that these are the waves that require a medium through which they can travel. So examples of these are water waves, sound waves are all mechanical waves. Now the ones that do not require a medium are called electromagnetic waves. So these are waves such as visible light that do not require a medium. So best example of this is visible light coming from the sun. So the light that travels from the sun does not require any mediums because there is no medium in space, but the light does travel through the space to come to hit on the Earth's surface. So there are two types of waves that we can think of, three types of waves. So a wave that consists of a single traveling pulse, we call that a pulsed wave. Whenever the source of wave motion is periodic motion, such as repeated motion of a hand moving up and down repeatedly, so we call that a periodic wave. And a final one, a wave whose source vibrates with simple harmonic motion, we call that a sine wave. So a sine wave is a special case of periodic wave in which the periodic motion is simple harmonic. So let's talk about two types of wave types. So first one is a transverse wave and a longitudinal wave. So there are two types of waves that we generally discuss. One is a transverse wave. The second is a longitudinal wave. So transverse wave and longitudinal wave are based on the fact that we have two main factors that affect wave motion. One is the vibration and the direction of propagation. So when you take a transverse wave, a best example of a transverse wave is a sine wave. So in a sine wave, notice that the vibration is happening up and down while the wave moves in perpendicular to that direction. So the wave motion is in this direction while the vibration is moving in this direction. So if the amplitude is perpendicular to the wave motion, we call that a transverse wave. Next one example is a longitudinal wave. So longitudinal waves travel in such a way where the amplitude and the velocity are in the same direction. So which basically says that the vibration and the direction of propagation are in the same direction. Let's take an example of a sound wave. So a sound wave generally has compressions and rarefactions, compressions and rarefactions, compressions and rarefactions. So notice that this here represents a compression, and the place where the density is very less, we call that a rarefaction. So notice that the vibration is in this direction, so where you have plus A and minus A, and the wave also is moving in the same direction. So the wave is also moving in the same direction and parallel to the direction of the vibration. So this is an example of a longitudinal wave. So best example of a longitudinal wave is a sound wave. So this here is a representation of a sound wave. So sound waves travel in the form of compressions and rarefactions. So an example of a transverse wave is a water wave on a pond, or a light wave. So all of these are examples of transverse waves. So notice here that we call the upper part, the maximum displacement in the positive direction, a crest, and the maximum displacement in the reverse direction, a trough. So transverse waves go in the forms of crests and troughs, and sound waves travel in the form of compressions and rarefactions. So again, what is the frequency of a wave? So frequency of a wave basically tells you the number of waves that pass a given point in a unit of time. The period of a wave is basically the amount of time it takes for one complete wavelength to pass a given point. So what is a wavelength right here? So wavelength basically includes one crest and one trough. For a sound wave, it includes one compression and one rarefaction. So the combined part is basically called as the period of a wave. Now the relationship between period and frequency in SHM holds true for waves as well as the period wave is generally inversely related to its frequency. Again, the wavelength is either between two tops or the length of entire one cycle of a wave. We call that the general wave. So there is a good relationship between the frequency of a wave and its wave speed. So the speed of a mechanical wave is constant for any given medium, and the speed of a wave is given by the following equation: V equals F lambda, where F represents the frequency and lambda represents the wavelength, and V here represents the wave speed, and this equation applies to both mechanical and electromagnetic waves. Now let's talk about waves and energy transfer. So waves transfer energy by the vibration of matter. So waves are often able to transport energy efficiently, and the rate at which a wave transfer energy depends on the amplitude. So the higher the amplitude, the higher the amount of energy that is being traveled in a given interval of time. So for a mechanical wave, the energy transferred is proportional to the square of the wave's amplitude, and the amplitude of a wave generally gradually diminishes over time as its energy gets dissipated. So with that, we end section 3. We'll talk about wave interactions in the next.